Hello, everybody. Today we'll be talking about GANs, which are generative adversarial networks. We'll be talking about some history of GANs, the theory of GANs, and some applications. You may have seen some examples of GANs in real life and not have realized what they were or how they work, so hopefully you'll walk away with a better understanding of how they work today. So we'll start off with some history. GANs were successfully implemented in 2014 by Ian Goodfellow, seen right here. They're a relatively new field of research in AI. They were developed while Ian was pursuing his PhD in machine learning at the University of Montreal in Canada. And what Ian wanted to do was create a new model that was generative. An AI model that could create images based on inputs where the output was believable and intentional. There were some models in the past that could do this, but they always produced outputs that weren't very good, and it was very obvious that they were created by a machine. So GANs are pretty controversial due to their subversive and potentially unethical applications. We'll get into that in a little bit, but I want to talk about what GANs are. So a GAN is an unsupervised machine learning model. And I use quotations around unsupervised because while it is unsupervised from an outward perspective, there is an internal supervision system built into the GAN. GANs are also generative. As I said, they create data sets based on input. These are usually images, but they can also be text or video. And GANs can be described as a game between two networks. So when I say that they're a game, what I mean is there's two neural networks playing against each other, and they're playing in a zero-sum game. So one network is trying to maximize its score, while the other network is trying to minimize the score of the other network. So how this works is summed up in a very nice way by Ian Goodfellow himself in a paper where he describes GANs as a game between counterfeiters and police. In this game, the input is a large set of money. It could be all of the money in the United States. And one network can be considered a counterfeiter, and the other network would be considered a police force. So the counterfeiter attempts to make fake money that will circulate with the real money and can be used just like real money is used. The other network, which is the police force, wants to attempt to lessen the counterfeiter's gains by finding and destroying the fake money. So the police force wants to find all of this fake money, remove it from the entire data set, but it also wants to make sure that it's not destroying the real money in the process. So the goal of the counterfeiter is to make as much money as possible that looks just like real money as to trick the police force so that they can't discriminate between the two. So some examples of GANs you may have seen in real life are deepfakes and face aging. These are probably some of the more popular applications you may have seen on social media. But basically here, we have two images that were generated by GANs. For the Obama images, there was an input that was Obama's face, and there's an input that is the CGI modeled face to the left of his face. So the output of the GAN is an image of Obama's face that looks realistic, but it's not quite true because he never made that face. That face was imposed by the counterfeiter GAN, and it tried to create an output where both of the inputs existed in the same output set. You can see this with the face aging example. I don't have the old person who was used in this example, but you can see an example of the real person's input face and how it turned out here on the right. Some of the many real-world applications of GANs are speech synthesis, which involves text-to-speech, speech recognition, and even emotion recognition. And medical imaging is also another application of GANs, specifically for the purpose of diagnosing. Another interesting application of GANs is video prediction. We won't talk about that in this slide, but basically a still frame from a video will be analyzed by a GAN, and then based on all of the previous inputs, all the previous frames of the video, the GAN will predict what the next frame of the video will be, and it will do this in succession. Now, I imagine that if you did this so many times, the video would become highly unstable, but it's an interesting application. And another application that we won't talk about today is cybersecurity, where a GAN can create a bunch of falsified data, and the discriminator, or the police force GAN, as we talked about earlier, will learn how to discriminate against those fake data sets and better learn how to protect a network. Have you ever seen one of those criminal investigation TV shows where they have maybe someone committing a crime or a piece of evidence on camera, and it's a really blurry video, so they use a enhance feature, which is very sci-fi and didn't exist at the time many of those shows were created? Well, a super resolution GAN can actually handle something like that. It uses two methods to reconstruct images with an optimized resolution. The methods are image denoising and super resolution reconstruction. GANs are somewhat ideal for this because the time complexity for resolution in this case is much more desirable than some other methods. GANs can handle both of these processes more efficiently because they're doing them at the same time rather than one after the other. Some drawbacks to this, though, is unstable network training and slow convergence. There's a lack of control of the model since training and validation is all self-handled by the GAN. And it's important to note that the output of this will never be as good as a real photo of what you're trying to optimize. So while it can enhance images that have been compressed or distorted, they will never be as good as a clear photograph. And next, we're going to be talking about the theory behind GANs.
Now we will discuss the theory of GANs, or generative adversarial networks. They are described as generative, as GANs can produce data that did not previously exist. The final goal of GANs is to be able to produce generated data that is indistinguishable from real data. They're described as adversarial because there's a generator and a discriminator which compete against one another as the network is trained. And they are called networks because both the generator and discriminator are neural networks. The first of the neural networks is the generator. Noise is the input into the generator. From this noise, the generator is able to produce a fake dataset. This fake dataset is passed on to the discriminator, which tries to determine whether or not the data is real. The generator then receives feedback on its performance of fooling the discriminator, thinking its dataset was real. Using this feedback, the generator updates itself to produce better data sets that are closer to the actual real data. The second neural network is a discriminator. The discriminator receives a real data set and tries to label the data either real or fake. Then it also receives a set of generated data from the generator and tries to also label it real or fake. The discriminator then evaluates its own performance and uses this feedback to update itself to be able to better categorize the data into either real or fake data. Two networks are the generator and discriminator. The generator provides the discriminator with a set of generated or fake data. It produces this data after noise is passed through the generator and passes on this fake data to the discriminator. A set of real data is also passed into the discriminator, and then the discriminator goes through all the data and tries to label it either real or fake. Since it's known which data is real and which data is fake, the performance can be evaluated. A discriminator loss occurs when the discriminator incorrectly classifies real data as fake or fake data as real. The generator has a loss anytime that the discriminator is able to tell that its fake data is fake. From the discriminator loss, the feedback can be sent back into the discriminator. Using backpropagation, the values inside the discriminator are adjusted so that the discriminator can better tell which data is real, which data is fake. Similarly, there's a feedback loop from the generator loss to update the generator values so that it can better produce data that the discriminator will not be able to determine is fake. This is the cost function of the GAN. D of x represents the probability as determined by the discriminator of a set of real data being real. D of g of z is the probability as determined by the discriminator of a fake data set, which is produced by the generator, of being real. The first term in the function is the expected value that a set of real data is real. The discriminator wants this value to be as high as possible, so it must maximize this. The second term is the expected value of 1 minus the probability that a fake data set is real. D of g of z is higher the more the discriminator is fooled by the generator into thinking fake data is real. Thus, the discriminator wants to minimize the value of d of g of z, or in other words, maximize 1 minus d of g of z. Thus, the discriminator wants to maximize the GAN function. The first term in the function is not affected by the generator. The second term, d of g of z, should be maximized by the generator. Since the function contains 1 minus d of g of z, the generator wants to minimize the function. Thus, we have a zero-sum game where the generator wants to minimize the function and the discriminator wants to maximize it. These are the steps of training the GAN. First, the architecture of the neural networks must be designed based upon the specific application of the GAN. Noise is transformed into data using the generator. This will serve as the fake data set. The discriminator is trained with both real and generated data. The discriminator must determine whether or not each data set is real or fake. Once the discriminator labels the data, its performance is evaluated. The discriminator's properties are then adjusted to maximize the cost function, or in other words, to better categorize real data as real and generated data as fake. The generator once again passes generated data into the discriminator. This time, after the discriminator parses through the data and labels it either real or fake, the generator's properties are adjusted. These properties are adjusted to minimize the cost function, or in other words, to better fool the discriminator that the generated data is real. Then this cycle continues over and over again. Steps to train the GAN are continued for many cycles. Eventually, the discriminator can no longer distinguish between the real and the generated data. At this point, the probability that generated data is real or fake is 50-50. The generator can now be used to generate fake data, which is similar to the real data.
These are two different applications for generative adversarial networks. First one, we have text-to-image synthesis. What this is it requires a text prompt from the user on whatever it is. On the example picture on the right, we have two prompts that are about birds of some color and size and feature, and as you can see, the generative adversarial network produces a range of images that the user can select. And you can also see that related to the second point there about iterative feedback, the prompt for the second picture on the right there does not specifically refer to a bird. It says this magnificent fellow. So you can see that that's likely interrelated between the two prompts. This was an iterative process of the user getting a picture of a bird in the first one and wanting to change to someone else, but the generative adversarial network being able to take into consideration the last prompt and change details about it in order to meet the user's needs. This is useful for a lot of reference artwork for artists because it's very quick and non-labor intensive, as well as for advertising and website creation and everything. And even some designers who may not be traditionally instructed in art will be able to at least generate some sort of image in order to communicate what they want their product or idea to look like. Again, without having to have practice drawing for years before the fact in order to get that. So just related to accessibility for those sort of applications. And the actual technical side of this is you have the generator and the discriminator. They're both trained on the same data set of images and corresponding descriptions, so that the generator is learning how to create what images correspond with which descriptions and how to create images that are related to that. And then the discriminator is trained to try and find the difference between something generated by the generator and something within the data set, as well as once it starts to produce images, the generator starts to produce images on its own, that the images the generator is producing are actually related to the prompt. So the discriminator sort of has two responsibilities there, as opposed to the general GAN style where the generator produces something, usually an image, and the discriminator just says whether it's fake or not. The second application we have is computer-aided diagnoses. Now, technically, computer-aided diagnoses are a type of program already used, not related to GANs, used in radiology and with x-rays in order to lessen workload on radiologists, to make things cheaper and faster and more reliable, where professionals can get a second opinion from this. The problem is that with some rarer health issues, the data set that the CAD programs, which I'll refer to them as CAD for the rest of this, are trained on, so things like you can see on the right, lung lesions, fractures, some of those do not have large enough data sets for CAD programs to be trusted by professionals. So GANs here are used to generate synthetic images of chest radiographs that are high res and very similar to the real images. So the technical side here is The generator is trained on the existing radiograph images, and this is a number of different health issues. This is not just for one or two. So the generator is trained on that. The discriminator is trained to distinguish between the real and the fake. And once the generator is trained well enough that the discriminator is being tricked much of the time, these generated images can be used to supplement the data sets that are being used to train the CAD programs, so that they have a wide enough range of images to accurately identify these issues when provided a radiograph image. Now, something notable here is that the GAN here needs to be trained on real images. Like, you cannot feed the GAN images back into the GAN in order to have a larger data set to train it on, because that will introduce a sort of synthetic bias where maybe just weirdness within the GAN will multiply within itself and become more prominent. So in order to ensure that that sort of bias is not introduced into these CAD programs, these GANs need to be trained on real images and a diverse range so that they're able to produce many diverse images for all these different health issues, and so that once these images are used to supplement the real data sets for CAD training, that these CAD programs are being trained on images that look real, but also not just the same kind of single image. Like, there is a ranging set of images for each issue, and then the CAD program can be trained on those and be better usable as a tool for radiologist professionals.